got music? What are we doing? There we go. So broken. All right, what are we doing? In the previous chapter, you created a Vulkan project with all of the proper configuration and tested it with a sample code. Yes. In this chapter, we're starting from scratch with the following code. Okay. Whoops. Alright. Control A doesn't work. Okay, main Vulkan 001. So let's save this as 002. Oh, it's not in that repo. Now we go all, paste. Now we got this thing. Save that. Whoops, computer. Are we... Sorry about that. So anyways, you didn't miss much. All I did was I read this and I copied and pasted this into the thing. Okay, so it doesn't even say compile yet. We first include the Vulkan header from the Lunar G SDK, which provides the functions, structures, and enumerations. Okay. The std accept and iostream headers, yes, std accept and iostream headers are included for reporting and propagating errors. I love propagating errors. It's so great. Don't you? The cstdlib header provides the exit success and exit failure macros. It does? Exit failure macro 1. Exit failure macro 0. Okay. Alright. And people think this is difficult. This is why programmers are viewed as like... Sorry. Okay. The program itself is wrapped into a class where we'll store the Vulkan objects as private class members. Oh. And add functions to initiate each of them. Right. Which will be called from the init Vulkan function. Cool. Init Vulkan. Oh. So that's going to grow. Once everything has been prepared, we enter the main loop to start rendering frames. Oh. Oh. We'll fill in the main loop function. Oh, there's a main loop function. Yes. Yes, Jeff. To include a loop that iterates until the window is closed in a moment. Oh. Once the window's closed and the main loop returns, we'll make sure to deallocate the resources we've used in the cleanup function. If any kind of fatal error occurs during execution, then we'll throw a std runtime error exception, excuse me, with a descriptive message, which will propagate, oh here we go, propagate, back to the main function and be printed to the command prompt. To handle a variety of standard exception types as well, we catch the more general std exception. One example of an error that we will deal with is finding out that a certain required extension is not supported. Roughly every chapter that follows after this one will add one new function that will be called from init Vulkan, and one or more new Vulkan objects to the private class members that need to be freed at the end in cleanup. Okay. So init Vulkan main loop cleanup. I am with you, Cheech. Okay. Just like each chunk of memory allocated with malloc, which I have never used in my life, never, not once, requires a call to free. Okay? Every Vulkan object that we create needs to be explicitly destroyed when we no longer need it. In C++, it is possible to perform automatic resource management using RAII, or smart pointers provided in the memory header. Okay. Whatever that is, whatever that was. Whatever RAII is, and whatever smart pointers are. However, I've chosen to be explicit about allocation and deallocation of the Vulkan objects in this tutorial. Oh, that's good. After all, Vulkan's niche is to be explicit about every operation to avoid mistakes, so it's good to be explicit about the lifetime of objects to learn how the API works. Okay, that's my goal. After following this tutorial, you could implement automatic resource management by writing C++ classes that acquire Vulkan objects in their constructor and release them in their destructor. Oh, that's a great idea. That's a great idea. Isn't that a great? That's a great idea. That's a dia with an I before it. It's a great idea. A dia with a great I before it. Okay. Or by providing a custom deleter. Ooh, custom deleter. To either std unique pointer or std shared pointer. Oh. Depending upon your ownership requirements. Again, we're with the pointers, you know. RAII is the recommended model for larger Vulkan programs. But for learning purposes, it's always good to know what's going on behind the scenes. So what is RAII? Since there's a link here. Excuse me. Resource acquisition is initialization. Is a programming idiom used in several object-oriented, statically typed programming languages to describe a particular language behavior. In RAII, holding a resource is a class invariant and is tied to object lifetime. Resource allocation or acquisition is done during object creation and by the constructor, while resource deallocation is done during object destruction by the destructor. That's what he just said. In other words, resource acquisition must succeed for initialization to succeed. Thus, the resource is guaranteed to be held between when initialization finishes and finalization starts. Holding the resources in a class is a class invariant and to be held only when the object is alive. Thus, if there are no object leaks, there are no resource leaks. RAII is associated most prominently with C++, where it originated, but also D, Ada, Vala, and Rust. The technique was developed for exceptions blah, 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 we go on. Okay, close tab. Thank you. All right. And that, my friends, is RAII. I like it. Okay. After following this tutorial, Vulkan objects are either created directly with functions like vkcreate or star, or allocated through another object with functions like vkallocate. They're created directly with create or allocated through another object with functions like allocate. Okay, that makes sense. After making sure that an object is no longer used anywhere, you need to destroy it with the counterparts, destroy or free. Right, so destroy, for create, and free. Okay. The parameters for these functions generally vary for different types of objects, but there is one parameter that they all share, p-allocator. Oh. This is an optional parameter that allows you to specify callbacks for a custom memory allocator. Oh. We will ignore this parameter in the tutorial and always pass null pointer as an argument. Okay. Ignoring, but we are aware. Alright. That's the point, I guess. All right. Vulkan works... Here, I guess we could... No, I don't want to do that. Vulkan works perfectly fine without creating a window if you want to use it for off-screen rendering. But it's a lot more exciting to actually show something First, replace the include Vulkan H line with this. Do we have a Vulkan H line? We do. Why do we have a Vulkan H line? Well, that was our, now we're why are we replacing? First of all, this program does nothing, so can we run it and it's fine? Yes. This program does nothing. Alright. Include GLFW, or define GLFW. Oh. So let's go like this. We're taking this, I guess. GLFW include Vulkan. I didn't know you could do that with GLFW. Apparently, there are a great many things you don't know. Well, wait, we're getting ahead. I was just reading ahead. Hold on. That way, GLFW will include its own definitions. Oh. And automatically load the Vulkan header with it. Oh. Add an init window function, and add a call to it from the run function before the other calls. Okay, init window. Init window. Adding it to the run. There we go. So we added the function, added a call to the run. Okay, didn't do anything. Very exciting. Very exciting. The very first call in init window should be GLFW init. Which initializes the GLFW library. Because GLFW was designed to create an OpenGL context, we need to tell it to not create an OpenGL context with a subsequent call. Oh. No API. Because handling resized windows takes special care that we'll look into later, disable it for now with another window hint call. Okay. All that's left now is creating the actual window, add GLFW window, private class member, to store a reference to it and initialize the window with that. Okay, I can do that. So the very first call in init window should be GLFW capital I, GLFW capital I init, like that. Oops, without the misspelling. Okay, apparently we're good there. This is cool. We're getting there. We've got 2 function calls. It's so exciting. Very exciting. Can we get a golf clap? Oh, we may. We may be adding golf claps to this. So non-resizable. So this is not Nook friendly. I have to remember that, but I'm sure they'll cover that later on. Okay, so here we're going to use this. Window equals GLFW create window. 800 by 600. Okay. And oh yeah, we have a squiggly because we need a let's see, where did he say to put it? Add a GLFW window private class member. Okay. Did I grab a space as well? Private class member, so. We're getting there. Very exciting. Excuse me. The fourth parameter allows you to specify. It's a good idea to use constants instead of hard-coded width and height numbers, because we'll be referring to these values a couple of times in the future. I've added the following lines above to the above the hello triangle application class. Okay. This is a hello triangle application class? Oh. Wasn't even paying attention. Pay attention. How much does it cost to pay attention? Okay, so far so good. We're very excited. It's very exciting. Very exciting. You should now have an init window function that looks like this. Yes, yes we do. To keep the application running until either an error occurs or the window is closed, we need to add an event loop to the main loop as follows. You mean we don't already? Hmm. There we go. GLF window should close. It's similar to what I've got in the OpenGL. Okay. Alright. Okay. Alright. Okay. This code should be fairly self-explanatory. It loops and checks for events like pressing the X button until the window has been closed by the user. This should also loop to where they have to call the function later in a single frame. Once the window is closed, we need to clean up first of destroying the terminating gems. This will be our first cleanup code. Oh, our first cleanup code. Oh. It's so cute. Our first little cleanup code. Coochie coochie coo. Alright. Having too much fun. Having too much fun. When you run the program now, you should see a window titled Vulkan show up. Until the application is terminated, now we've taken the skeleton of Vulkan. Let's create our first Vulkan object. C++ code. What's this? Oh, do they give you the whole code and everything? You mean I could have just copied? Alright. Alright, I'm fine. There you have it, though, for those following along. You could have just clicked right there. Everything would have been fine. But let's run it, make sure it works. No errors. It should say Vulkan window. It's a Vulkan window. Live long and prosper. Let's update the window. A Vulkan window. Live long and prosper. Yes. There you go. I had to do it. I have to do it. I had to do it. You have to include it. When you're working with Vulkan, how can you not? Alright. Alright, well, I don't know. I suppose I should fix some food. And then I can do a little bit more of this. Yeah, I mean, I know I'm going to be hungry eventually, right? So, okay, creating an instance. Oh, there's just a lot of comments at the end. Okay. So, alright, well, I could follow along and read it. This isn't that far along, or far down. It's just right down to there. Okay, let me go start some food. I will come back. And we're in Vulkan. Captain, we must proceed with more Vulkan. Captain. Yes, Spock, I agree. Okay, creating an instance. The very first thing you need to do... Wait, we've already done first things. What? What? What happened? The very first thing... Okay, to initialize the Vulkan library. Oh, initialize the Vulkan. Oh, and that's the Vulkan library. So it's kind of like beaming down to Vulkan. We're kind of like beaming down to the planet, seeing what's going on, figure out what's going on. Okay. Is initialize the Vulkan library by creating an instance. Wait, what happened to beaming? I want to beam. We've got the transporter. We've got Scotty. I can't beam you, Captain. You're just gonna have to get to Vulkan by shuttle. Alright, sorry. The instance is the connection. Oh, connection. Oh. That sounds kind of intimate. I'm not sure I'm ready for that with Vulkan. Between your application, oh, and the Vulkan library. Oh, so I'm kind of setting them up. So it's really kind of like I'm matchmaking for them, for the application and the Vulkan library. Okay, alright. And creating it involves specifying some details about your application to the driver. Wait a minute, application, Vulkan library, the driver's going to get involved too? Start by adding a create instance function and invoking it in the init Vulkan function. Oh. You know, I could copy the code from the bottom, but I'm thinking I want to just step by step it. Okay, so init Vulkan, we're going to put a create instance function, which means that we also have to create a create instance function, right? Right? Private VK instance. Additionally, add a data member to hold the handle to the instance. Oh, so it's like a pan. Oh, hold the handle. All right. VK instance. There we go. Now we've got the private window and we've got the private VK instance. Very exciting. It's very exciting. Now to create an instance, we'll first have to fill in a struct. Wait a minute, fill in a struct. That sounds like Windows programming. Windows. Oh, here we go. Look at that application info structure. Oh, Windows programming. I bet you Microsoft is behind this whole thing. Fill in a struct with some information about application data is technically optional, but it provides some use from the driver in order to optimize the application because he uses well-known graphics and search behavior. The structure is called VK application info. Create instance. All right. So that is the name of the function, and it gets a VK application info, app info, and then it does the thing right there. And then it does the app info S-type, VK structure type, application info, application name, hello triangle, application version, VK make version 1, no engine, engine version VK make version 1, API version, VK API version 1_0. So can I change those and choose the version later? Is that what we're doing? This is a major minor patch. Oh, cool. Deprecated. VK make API version should be used instead. What? Hey, wait a minute. I'm following this tutorial. Do you mind? Make API version. Oh my goodness. Oh my goodness. Looks like it's exactly the same. It just has a different name. Make underscore API. We're updating, folks. We're updating. Oh, and it has a variant. So what are we putting in for variant? I don't know, let's go back to the other one. I'm scared. Alright, until we learn something to put in for variant, probably 0, but whatever. But what ifs? Okay, okay. As mentioned before, many structures in Vulkan require you to explicitly specify the type in the S-type member. This is also one of the many structs with a p-next member that can point to extension information in the future. We're using value initialization here to leave it as null pointer. We are. A lot of information in Vulkan is passed through structs instead of function parameters. And we'll have to fill in one more struct to provide sufficient information for creating an instance. This next structure is not optional and tells the Vulkan driver which global extensions and validation layers we want to use. Global here means that they apply to the entire program and not a specific device, which will become clear in the next few chapters. The first two parameters are straightforward. So does this go into the create instance or the init Vulkan? I think we're still creating the instance. So instance create info. Create info.s-type, vk structure type instance create info p application info app info. Oh, so it takes everything we just did here and puts it right there. Oh. So wait a minute. Create info.p application info.s-type. So we could have just filled it in right there that way. We could have just created just the VK instance and then filled in the p application info with that. All right. Version 2. The first two parameters are straightforward. The next two layers specify the desired global extensions. As mentioned in the overview chapter, Vulkan is a platform agnostic API, which means that you need an extension to interface with the Windows system. You need an extension to interface with the Windows system. GLFW has a handy built-in function that returns the extensions it needs to do that which we can pass to the struct. So we're still building our create info. Okay. Now we've got this extension count equals 0. Const char pointer GLFW extensions. GLFW extensions equals GLFW get required instance extensions. GLFW extension count. Create create info enabled extension count. Create info PP enabled extension names, GLFW extensions. Oh, so it gets an array of the names of the extensions. Oh, that's cool. Huh. Cool. Okay, this is working out pretty well. The last two members of the struct determine the global validation layers to enable. We'll talk about these more in depth in the next chapter, so just leave these empty for now. Create info.enabled layer count equals 0. We've now specified everything Vulkan needs to create an instance, and we can finally issue the vk create instance call. Okay, so let's just go here. Create info enable layered count. And then vk result equals vk create instance. Hold on. VK create instance, create info, that gets thrown in, and it's filled in with stuff. So is instance. Just a pointer is sent in, okay. And then null pointer, so result, okay. As you'll see, the general pattern for object creation function parameters in Vulkan follow is pointer to structure with creation info, pointer to custom allocator callbacks, always null pointer in this tutorial, pointer to the variable that stores the handle to the new object. If everything went well, then the handle to the instance was stored in the VK instance class member. Nearly all Vulkan functions return a value of type VK result. That is either VK success or an error code. To check if the instance was created successfully, we don't need to store the result and can just use a check for the success value instead. Oh. So you can call it this way, or you can call it this way with a if and a throw and all kind of stuff. Okay. So wait, we're not doing a catch throw. Wait. Are we? Throw std runtime error failed to create instance. Huh, so will that work? Now run the program to make sure the instance is created successfully. Oh. Well. Succeeded, live long and prospered. No errors, we're good. Huh. Encountered VK error incompatible driver. If using macOS with the latest Molten VK SDK, you may get VK error incompatible driver returned from VK create instance. According to getting start notes, beginning with the 1.3.216 Vulkan SDK, the VK KHR portability subset extension is mandatory. To get over this error, first add the VK creative instructions. Typically the code would be like this. Okay. Checking for extension support. If you look at VK create instance documentation, then you'll see that one of the possible error codes is VK error extension not present. We could simply specify the extensions we require and terminate if that error comes back. If that error code comes back. That makes sense for essential extensions like the Windows System Interface, but what if we want to check for optional functionality? To retrieve a list of supported extensions, I wasn't able to start my food yet. I had to go clean stuff, so I'm going to go back in a minute and start food. Hold on, I got to drink some. But that makes sense for essential extensions like the Windows system. But what if we want to check for optional functionality? Oh, I'll probably never do that. However, to retrieve a list of supported extensions before creating an instance, there's the VK enumerate instance extension properties function. It takes a pointer to a variable that stores the number of extensions and an array of VK extension properties to store details of the extensions. It also takes an optional first parameter that allows us to filter extensions by a specific validation layer, which we'll ignore for now. To allocate an array to hold the extension details, we first need to know how many there are. You can request just the number of extensions by leaving the latter parameter empty. Extension count, VK enumerate instance, are we going to do this? Now allocate an array to hold the extension details, include a vector. Finally, we can query the details there. Extensions.data. Each VK extension property struct contains the name and version of an extension. We can list them with a simple loop. You can add this code to the create instance function if you'd like to provide some details about the Vulkan support. As a challenge, try to create a function that checks if all of the extensions returned by GLFW get required instance extensions are included in the supported extensions list. Excuse me. So what are we trying to do? Just put all this code in? The VK instance should be only destroyed right before the program exits. It can be destroyed in cleanup with the destroy instance function. Okay, so let's put that in cleanup right before the GLFW destroy window. Save it there. let's look at this stuff here. The parameters for the VK destroy, and we're done. Okay. The parameters for the VK destroy instance function are straightforward. As mentioned in the previous chapter, the allocation and deallocation functions in Vulkan have an optional allocator callback that we'll ignore by passing null pointer. All of the other Vulkan resources that we create in the following chapter should be cleaned up before the instance is destroyed. Before continuing with the more complex steps after instance creation, it's time to evaluate our debugging options by checking out validation layers. Okay, so let's try this code real quick. Although, did they put that in here? No. Okay. So create instance. Don't we just put it up here though? Because here we've created the, if you look at the create instance documentation, to retrieve a list of supported extensions before creating an instance, there's the VK enumerate instance function. Oh, so before creating an instance. Okay, so extension count. Here's extension count, the extensions, get required extensions. So let's comment this stuff out here real quick. And then just put this in. So we already have, oh, I see, he used a different variable, that's fine. So extension count, VK enumerated, okay. So far I'm with you. I'm with you. STD vector, we're just going to create a temporary vector. And it's a vector of VK extension properties. Does that mean we have to go up here and include vector? Like that? Okay. Excuse me. And then we call this, finally we can query the extension details. So then we go here. So that takes this extension count, sends it in, and it also sends in extensions.data. Is that a pointer? Local variable, yeah, extensions. So that's a pointer to that data. Interesting. Each VK extension properties struct contains the name and version of an extension. We can list them with a simple for loop. /t is a tab for indentation. Oh, okay. std out available extensions const auto extension : extension. I think that's a thing. Std out tab extension name. Well, let's run that and see what's available. Oh, that's cool. Look at that. Available extensions: device group creation, external fence capabilities, external memory capabilities, external semaphore capabilities, get physical device properties, get surface capabilities, get KHR surface, Win32 surface, extension debug report, extension debug utils, swap chain color space. Okay, interesting. Well, I mean, that doesn't really interfere with the instance creation, so none of these variables are referenced. So we can then we can call that, we can do that, and then we can do that and then create our instance. So you can do it all at the same time. And then we've got that just showing in the debug window. That's not bad, not bad. So this is the create instance function. Let's take this and go show available extensions, because I'm sure we'll never use it. And I just want to get it out of the create instance function. So we'll go void show available extensions. Okay, and then we're just going to call it now. Do we need anything from? We don't. Okay, so floop, and then we can go here and go floop like that, and it doesn't need any variables. So then I can either comment that or this we can just do optional right there. Okay, so that works really well. I really like that. We've got this go in the create instance, and that's it. We're done with this chapter, cleaning up. Okay, so next is validation layers, whatever that is. What are validation layers? Yes, I need to know, because I don't know. Alright, I'm going to go fix food. I'll be right back. Okay, food's on the way, so we got at least a half an hour. Okay, what are validation layers? How's the music? We doing good? What are we doing? Alright. Solitude. Okay. The Vulkan API is designed around the idea of minimal driver overhead, and one of the manifestations of that goal is that there is very limited error checking in the API by default. Okay. Even mistakes as simple as setting enumerations to incorrect values or passing null pointers to required parameters are generally not explicitly handled and will simply result in crashes or undefined behavior. Because Vulkan requires you to be very explicit about everything you're doing, it's easy to make many small mistakes. Like using a new GPU feature and forgetting to request it at logical device creation time. Interesting. However, that doesn't mean that these checks can't be added to the API. Vulkan introduces an elegant system for this. What? Known as validation layers. Oh, cool. Tell me more. Validation layers are optional components that hook into Vulkan function calls to apply additional operations. Common operations in validation layers are checking the values of parameters against the specifications to detect misuse, tracking creation and destruction of objects to find resource leaks, checking thread safety by tracking the threads that calls originate from, logging every call and its parameters to the standard output. That's cool. Tracing Vulkan calls for profiling and replaying. Because logging every call and its parameters to the standard output, that's what, what's his name was just talking about on his YouTube. That one guy, I can't remember his name at the moment. Randall. Tracing Vulkan calls for profiling and replaying. Okay, here's an example of what the implementation of a function in a diagnostics validation layer could look like. Okay, so it just checks for those required parameters. If they're null, then it says that's a required parameter, you can't pass null, and it gives an error. These validation layers can be freely stacked to include all the debugging functionality that you're interested in. You can simply enable validation layers for debug builds and completely disable them for release builds, which gives you the best of both worlds. Okay. Vulkan does not come with any validation layers built in, but the LunarG Vulkan SDK provides a nice set of layers that check for common errors. So we kind of went from worse to just bad, because it said worse earlier that it's possible to make many small mistakes. Now it says it checks for common errors. That's kind of good. Alrighty. They're also completely open source, so you can check which kind of mistakes they check for and contribute. Using the validation layers is the best way to avoid your application breaking on different drivers by accidentally relying on undefined behavior. Validation layers can only be used if they have been installed onto the system. For example, LunarG validation layers are only available on PCs with the Vulkan SDK installed. There were formerly two different types of validation layers in Vulkan, instance and device specific. The idea was that instance layers would only check calls related to global Vulkan objects like instances, and device-specific layers would only check calls related to a specific GPU. Device-specific layers have now been deprecated, which means that instance validation layers apply to all Vulkan calls. The specification document still recommends that you enable validation layers at the device level as well as for compatibility, which is required by some implementations. We'll simply specify the same layers as the instance at logical device level, which we'll see later on. Okay. Whatever that means. Good. Using validation layers. Okay, and so how much is this? Message callback gets into a bunch of stuff. This is pretty hefty. Debugging, instance creation, and destruction. Testing, configuration. Okay, so it goes to right about there. So this is a pretty hefty chapter. We'll see how far we get before food's ready. I'm hungry. I stop. Maybe we'll go until we're done. In this section, we'll see how to enable the standard diagnostics layers provided by the Vulkan SDK. How to enable the standard. Okay. Just like extensions, validation layers need to be enabled by specifying their name. All of the useful standard validation is bundled into a layer included in the SDK that is known as VK layer Chronos Chronos validation. Let's first add 2 configuration variables to the program to specify the layers to enable and whether to enable them or not. I've chosen to base that value on whether the program is being compiled in debug mode or not. The ndebug macro is part of the C++ standard and means not debug. If not debug, enable validation layers is false. Otherwise, enable validation layers is true. Okay. We'll add a new function, check validation layer support, that checks if all the requested layers are available. First, list all of the available layers using the VK enumerate instance layer properties function. Its usage is identical to that of VK enumerate instance extension properties, which was discussed in the instance creation chapter. So we're adding a new function. Okay. I can do that. And it is a bool. Or wait, we just defined it. It's so weird to actually define them right in the definition of the class. I'm used to having the function definitions be outside the class definition. Anyways. So that works. Check validation layer support, layer count, VK enumerate instance layer properties. So this is layer properties. Okay, layer count. Because this before what we did was extension properties. Alright. VK layer properties, available layers. This is a vector of VK layer properties called available layers, and then it's created with layer count, number of them. So that's cool. And then VK enumerate, and then this one. Oh, extension count. That's why this works. Okay. I gotcha. So you get the extension count first. So you're doing the same thing here. We're getting the layers, the layer count, and then we're populating that data with, yeah, enumerate instance layer properties. Oh, cool. So can we print those out as well? Validation layers, enable validation layers. Now check if all the layers in validation layers exist in the available layers list. You may need to include cstring for string compare. Cstring. All right. Check validation layer support. Okay. Check if all the layers and validation layers exist in the available layers list. You may need to include C-string of that. So for const layer name validation layers, bool layer found, const da 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 da. So what does this do? Oh, if enable validation layers and check validation layer support. Oh. So let's put this in. Validation layers. Why do they have this variable? Oh, it comes into use later. Oh, right here. Okay, so we're putting that in check validation layer support, right? I'm so kind of lost at the moment, just because maybe I'm hungry. Okay, so what were we doing? This, and then it's returning. So are we replacing this return false? To be either return true or false. Okay. So instead of return false, we're going to put in that. Return true. Go through this. And then validation layers. So what we need to do to make that work is this other code here. So this is defined all above, right up here. So it's defining a variable and setting its default value. And then this one is defining another constant called validation layers. VK layer Chronos validation. Okay. And that's going to be used, let's see, because this is called validation layers, which is right here. For const char layer name, validation layers. Layer properties in, oh, okay, so here's the real loop. String compare layer name, layer properties, layer name, okay. Layer found equals true, break. If not layer found, return false. So this will probably just only execute once. And otherwise it'll return true? Okay. We'll add a new function, excuse me, check validation layer support that checks if all the requested layers are available. First list all the layers using the VK enumerate instance layer properties function. Its usage is right. Okay, we got that. Check if all layers in that thing, then do that. We already did that. We can now use this function in create instance. Okay, so then we're going to go like this. In the create instance function. Where do we put it in the create instance function? Just at the end here? Validation layers are next, so yeah. If enable validation layers and check validation layer support, and not check validation layer support. Validation layers requested but not available. Okay, so otherwise it'll continue on. So I like the idea of a throw. That's kind of interesting. I didn't think you could do that without a catch, but that's all good. Now run the program in debug mode and ensure the error does not occur. If it does, then have a look at the FAQ. Finally, modify the VK instance create info structure and instantiation to include the validation layer names if they are enabled. Oh, well, let's run it first and then do what he said. Okay. Okay, no errors. Same list of extensions. That's cool. So let's go here. If enable validation layers. Right there. So if enable validation layers, create info enabled layer count equals validation layers dot size. Enabled layer count equals validation layers dot size. Create info pp enabled layer names equals validation layers dot data. Else create info. Okay. Create info. So is this all supposed to be before creating the instance or after? Because it's still populating create info. So let's go down here. Put this right there. And does he have code for this at the bottom? It's kind of a long one. Message callback. C++ code. Oh, okay, and then there's more that's added. Okay, so create info starts right there. Then it goes through this is extra stuff we haven't covered yet. VK create instance is the very last thing, right? That's what I thought. Okay. But those other things can be up here. Oops. S-type, application info, enabled extension count, get required extensions. Get required extensions. Is that a function that they make? Get required extensions. It is a function. So he just takes that and puts it into a function. That's cool. std vector const char, it returns a vector. Interesting, I like that. Get required extensions. Auto extensions, excuse me, auto extensions equals get required extensions. And then right down here, auto, std vector const char pointer get required extensions. Okay. So that takes care of this GLFW get required instance extensions. GLFW extension count is local just to this function. So is the const char GLFW extensions. Then it creates the return right here. Extensions, GLFW extensions plus extension count. Enable validation layers, extension, pushback, VKT, debug. So this function must get created probably during the tutorial here, the next section. Whoops, don't do what I just did. All right. Finally, modify the VK instance create info structure, and we did that, right? We have that. If enable validation layers. Yeah, we have those right there. Okay, so then we're right here. And he adds a bunch of... Oh, see, perfect. This is exactly what I was talking about. The validation layers will print debug messages to the standard output by default, but we can also handle them ourselves by providing an explicit callback in our program. This will also allow you to decide which kind of messages you would like to see, because not all are necessarily fatal errors. If you don't want to do that right now, then you may skip to the last section in this chapter. To set up a callback in the program to handle messages and the associated details, we have to set up a debug messenger with a callback using the VK extension debug utils extension. Yeah, I saw that. We'll first create a getRequiredExtensions function that will return the required list of extensions based on whether validation layers are enabled or not. Which is where that getRequiredExtensions function comes from. So now I can do that. Okay, so getRequiredExtensions, and we'll just, are we putting it at the top? Doesn't matter. Okay, so getRequiredExtensions returns the extensions. So now, of course, where does that go? So create instance, and then of course this is the next one. Okay, so here's the getRequiredExtensions, and then it is called right here. So auto extensions equals, and then extension, and so right here is where it's used. So it's, yeah. But there's going to be more from this chapter, so for now we can just take it and, wait, where does it go? Where does this go? So create info, it starts populating the create info. And then before it gets to the vCreate instance, right? Okay. So create info, and it starts populating it. Oh, it's right here. Extension count extensions, show available extensions. Get required, well, let's see what else here. I think it's just these two. Actually, then it should also be this call. Yeah, so this I believe happens inside the function. GLFW get required instance extensions. Yeah, GLFW get required instance extensions is moved inside the function here. And then it also does this thing which it's going to talk about, and then it gets, so yeah, so return extensions, and then auto extensions equals that, and then it and that's optional. So this is out now. And it doesn't do the, wait, what does it do here? This is already populated in the create info, isn't it? Let me see what he did. Which which ones? The enabled extension count and the PP enabled extension names. Maybe we don't use those anymore? Enabled extension count and PP enabled extension names. Oh wait, those already are put in by what I just did. Right, okay. Alright, I think I get that. Whew. And then this is taken care of by the that right there. So now we're down to, yeah, just that. Okay, interesting. I'm just doing this and to make sure I understand it and familiarizing myself with it, at least. I may not understand all this at the moment, but he says that we will also go through in the various chapters, because this is just the setup chapter. So, and then we've got this to go through, and then that happens. Okay. And then all this. Alright, I think we're good. So is this runnable at this point? Yeah. So it's good. It still shows the extensions and everything. We can do any other kind of... That's good. Okay. Okay. Well, I'm still waiting on food, so let's keep going. Message callback. So the get required extensions... The extensions specified by GLFW are always required, but the debug messenger extension is conditionally added. Note that I've used the VK extension debug utils extension name macro here, which is equal to the literal string VK extension debug utils. Using this macro lets you avoid typos. We can now use this function in create instance. Auto extensions equals get required extensions, create... Oh, I already have that. Run the program to make sure you don't receive a VK error extension not present error. We don't really need to check for the existence of this extension because it should be implied by the availability of the validation layers. Okay. Now let's see what a debug callback function looks like. Add a new static member function called debug callback with the pfn underscore vk debug utils messenger callback extension prototype. The VK API attribute and VK API call ensure that the function has the right signature for Vulkan to call it. Excuse me. We're adding a new static member function. And it's got this VK API. On Windows, Vulkan commands use the std call convention. VK bool 32, VK API call, std call. Interesting. So it's a macro with a return type sent into a macro. We're good. Everything's fine. Yeah, oh, and it tells you about it. Okay, so the first parameter specifies the severity of the message, which is one of the following flags. The first parameter? VK debug utils message severity verbose bit extension diagnostic message. Okay. VK debug utils message severity info bit extension informational message like the creation of a resource. Warning: message about behavior is not necessarily an error but likely a bug. Message about behavior that is invalid and may cause crashes. Okay, so it's kind of like, yeah, that reminds me of Windows error messages for the event system or whatever. The values of this enumeration are set up in such a way that you can use a comparison operation to check if a message is equal or worse compared to some level of severity. For example, if message severity is greater than VK-debug-util's message severity warning bit extension, the message is important enough to show. Oh, I see. Okay. The message type parameter can have the following values. The message type parameter. Oh, that's the next parameter in that function up here, because it's not right there. But so the message type is the next VK-debug-util's message type flag extension message type. Okay. Can have the following values. VK-debug-util's message type general bit extension. Some event has happened that is unrelated to the specification or performance. Okay. Validation bit. Something has happened that violates the specification or indicates a possible mistake. Okay. Performance bit. Potential non-optimal use of Vulkan. Okay. The P callback data parameter refers to VK-debug-util messenger callback data extension struct containing the details of the message itself, with the most important members being P message, the debug message as a null terminated string, P objects, an array of Vulkan object handles related to the message, and an object count, the number of objects in the array. Finally, P user data parameter contains a pointer that was specified during the setup of the callback and allows you to pass your own data to it. Okay. The callback returns a boolean that indicates if the Vulkan call that triggered the validation layer message should be aborted. The callback returns true, then the call is aborted with a VK error validation failed extension error. This is normally only used to test the validation layers themselves, so you should always return VK false. All that remains now is telling Vulkan about the callback function. Perhaps somewhat surprisingly, even the debug callback in Vulkan is managed with a handle that needs to be explicitly created and destroyed. Such a callback is part of a debug messenger, and you can have as many of them as you want. Add a class member for this handle right under instance. Okay. Now add a function, set up debug messenger to be called from init Vulkan right after create instance. Oh. We'll need to fill in a structure with details about the messenger and its callback. So set up debug messenger. Interesting. To be called inside of init Vulkan right after create instance. Set up debug messenger. We'll need to fill in a structure with details about the messenger and its callback. Okay. Oh, I see. Wow. Interesting. I kind of semi-understand that. Huh. So we're adding this to the new function, setup debug messenger. Oh my gosh. The insanity of it all. Bum, ba, ba, bum. If not, enable validation layers, return. Okay. The message severity field, hold on. allows you to specify all the types of severities you would like your callback to be called for. I've specified all types except for, oh, I see. So verbose, warning, and error. Okay. I've specified all the types except for info here to receive notifications about possible problems while leaving out verbose general debug info. Similarly, the message type. The message type field lets you filter which types of messages your callback is notified about. I've simply enabled all types here. Message type, general type, validation bit, performance bit. Oh, okay. I've simply enabled all types there. Here you can always disable some if they're not useful to you. Finally, the PFN user callback field specifies the pointer to the callback function, debug callback. You can optionally pass a pointer to the puser data field, which will be passed along to the callback function via the puser data parameter. You could use this to pass a pointer to the Hello Triangle application class, for example. Note that there are many more ways to configure validation layer messages and debug callbacks, but this is a good setup to get started with for this tutorial. Okay. See extension specification for more information about the possibilities. So debug callback, that's not, is that the name of our function that we just made? No. So are we going to create a function called debug callback here? This structure should be passed to VK create debug utils messenger extension function to create the VK debug utils messenger extension object. Unfortunately, because this function is an extension function, it is not automatically loaded. We have to look up its address ourselves using VK get instance procedure address. We're going to create our own proxy function that handles this in the background. I've added it right above the Hello Triangle application class definition. The VK get instance procedure address function will return null pointer if the function couldn't be loaded. We can now call this function to create the extension object if it's available. Okay, so we're just creating this function here, which does what? Instance, look at all those parameters. Okay. Auto function equals create. Wow. Okay. So it's just a function and it's outside of the Hello Triangle thing. So right up here, I guess. Okay. And then it gets called. We can now call this function to create the extension object if it's available. Oh, and that's not the only one. Okay, so create it and then destroy it. Okay. And then where is that called? Create debug utils messenger extension. Oh, right in here. Setup debug messenger. Oh, so in the setup debug messenger function. Oh, and this is in a separate function. Eventually. Alright. Well, that works. The second to last parameter is again the optional allocator callback that we set to null pointer. Other than that, the parameters are fairly straightforward. Since the debug messenger is specific to our Vulkan instance and its layers, it needs to be explicitly explicitly specified as the first argument. You will also see this pattern with other child objects later on. The VK debug utils messenger extension object also needs to clean up with the call to VK destroy debug util messenger. Similar to that, function needs to be explicitly loaded. Create another policy function right below create, and it's called destroy. Okay. I am so far with you, I believe. I believe. Why does it do that? Okay. That's crazy. This is crazy, but whatever. Make sure this function is a static class or function outside the class. We can then call it in the cleanup function. So, if enable validation layer is destroyed, okay. So in the cleanup function, we're going to add that, which is down here. Okay. Interesting. Debugging instance creation and destruction. Although we've now added debugging with validation layers to the program, we're not covering everything quite yet. The VK create debug utils messenger extension call requires a valid instance to have been created, and VK destroy debug utils messenger extension must be called before the instance is destroyed. This currently leaves us unable to debug any issues in the VK create instance and VK destroyed instance calls. However, if you closely read the extension documentation, you'll see that there is a way to create a separate debug utils messenger specifically for those two function calls. It requires you to simply pass a pointer to a debug VK debug utils messenger create info extension structure in the pnext extension field of VK instance create info. First, extract population of the messenger create info into a separate function. We can now reuse this in the create instance function. The debug create info variable is placed outside the if statement to ensure that it is not destroyed before the by creating an additional debug messenger this way, it will automatically be used during VK create instance tries to clean up after that. Okay. Testing. Now let's intentionally make a mistake to see if the validation layer is in action. Temporarily remove the call to destroy debug util messenger extension in the cleanup function and run your program. Once it exits, you should see something like that. If you want to see which call triggered a message, you can add a breakpoint to the message callback and look at the stack trace. There are a lot more settings for the behavior validation layers than just the flag specified in the VK debug utils messenger create info extension struct. Browse to the Vulkan SDK and go to the config directory. There you will find a VK layers settings text file that explains how to configure the layers. To configure the layer settings for your own application, copy the file to the debug and release directories of your project and follow the instructions to set the desired behavior. However, for the remainder of this tutorial, I'll assume that you're using the default settings. Throughout this tutorial, I'll be making a couple of intentional mistakes to show you how helpful the validation layers are with catching them and to teach you how important it is to know exactly what you're doing with Vulkan. Now it's time to look at Vulkan devices in the system. Okay, everybody? And here's what we're going to do. Just going to copy everything, paste it in there, and run it. Okay. Did he leave the errors in there? Or no, it's actually, wow, putting this all here. Okay, so that would be great to send to like a file so I could look at it. Validation layer device extension, load device, look at all this. Okay, I am amazed that we got through that chapter. We are going to the next chapter where it says next here. and it is physical devices and Q families. Notice that we're still a ways away from drawing. So I have that saved there. Let's take out base code. Let's delete that. And let's put this one where that was. Excuse me. And then I'll go back up here, take it, bring it all the way to the top. There we go. Okay. Alright. So that saves our spot. Vulkan, that's fine. That's the Vulkan there. Okay. Thanks everybody for watching. Phew. Wasn't that crazy?